Hello everyone. In this lesson, we will talk about the knowledge of Chapter 4 of Low-Frequency Electronic Circuits, Amplifier Basics. Next, we will introduce main performance characteristics of differential amplifiers. First, we will introduce the differential mode signal and common mode signal. Differential mode signal refers to the existence of a pair of similar size in opposite direction signals. Remember, Vi1 is equal to negative Vi2. The differential mode signal is expressed as Vi1 minus Vi2 equals Vid. Common mode signal means a pair of signals with the same size and same direction. We express it as Vic equals Vi1 equals Vi2. In the future, we will use Vid to represent the differential mode signal, Vic to represent the common mode signal. In double-ended input signals, input signal difference is differential mode signal Vid. The average value of the input signal is the common mode signal, expressed as Vic is equal to 1 out of 2 Vi1 plus Vi2. The following example is to illustrate that for two arbitrary input signals, all can be expressed as a differential mode signal and superimposed on the common mode signal. For example, Vi1 is equal to 10 volts, Vi2 is equal to 6 volts. We follow the previous definition. Common mode signal is equal to the average of the two signals. That is, Vic is equal to 8 volts. The differential mode signal is equal to the difference between the two signals. So, Vid is equal to 10 volts minus 6 volts equals to 4 volts. Then, for the signal on the left, we can express as common mode signal plus half differential mode. And for the right, we can express it as a common mode signal minus half Vid. In this way, two arbitrary signals can be expressed as a pair of common mode signals plus a pair of differential mode signals. The same is true at output. For each single-ended output, the difference between the two output signals in terms of VO1 and VO2 is called differential mode output signal. The average of two output signals is called common mode output signal, represented by VOD and VOC respectively. As shown in the picture, the general input signal can be understood as a pair. Common mode signals have the same magnitude and the same direction, and superimpose a pair of differential mode signals of equal size and opposite direction. Considering that the transistor works in the linear amplification region, the superposition theorem also applies. So we can divide it into differential mode circuit considering only the effect of differential mode signal, and the common mode circuit that only considers the effects of common mode signal. Differential and common mode circuits work together is the final result of the circuit. First, look at the differential mode circuit and the differential mode performance. At input with Vid1 and Vid2, so that the two are equal in size, differential mode signals in opposite directions. At this point, you can see the current they produce are positive IC and negative IC respectively. These two AC signals, then they cancel each other through REE. In other words, on REE, AC signal does not work. So, REE can be regarded as a short circuit. VEE can be seen as a public. After the REE in the circuit is regarded as a short circuit, the circuit form becomes the upper right picture. We draw the differential mode AC path. As we can be seen, the sum of the input terminal Vid1 and Vid2 forms the differential mode signal Vid. The The sum of the output signal VOD1 and VOD2 constitutes the output signal VOD. Because the circuit is symmetrical, we only ask for the performance of one of the cogeneration amplifiers, and we can get the differential mode performance of the differential amplifier. This analyze method is usually called half-circuit analyze method. For a cogeneration amplifier, input resistance is equal to RBE, output resistance is equal to RCE parallel RC. Control differential mode circuit, it can be seen that the input resistance RID at this time, it is equal to twice the input resistance Ri, that is equal to 2 times RBE. For single-ended output, the output resistance ROD1 at each end is equal to the output resistance of the primary amplifier, and it is also equal to RCE parallel RC. Output resistance ROD for double-ended output, it is equal to 2 times RO. It is equal to 2 times the RC parallel RCE. Let's take a look at the gain of the differential mode. For the first level cogeneration amplifier, its voltage gain is equal to the negative spin multiplied by RL. Let's analyze. Differential mode gain for single-ended output. Single output differential mode gain. The numerator is the output voltage at each end, VOD1 or VOD2. They are equal to 1 out of 2 VOD. And the denominator is the differential mode signal VID. Write the formula into this form: 1 out of 2 VOD and 1 out of 2 VID. It is the gain of the primary amplifier. So, for single-ended output, its voltage gain is equal to 1 out of 2. Single-stage amplifier gain, also know that because the voltage polarities of the two output terminals are opposite, so AVD1 and AVD2, the two gains are opposite to each other, and the size is equal to 1 out of 2 GMRL. And the whole differential mode gain, the differential mode gain of the double-ended output is equal to VOD divided by VID equal to negative GMRL. It can be seen that the differential mode gain of the double-ended output, the gain is the same as the single cogeneration amplifier. The following describes the common mode equivalent circuit and its performance characteristics. Common mode equivalent circuit refers to the two input terminals, plus equal size, common mode signal VIC in the same direction. Under these circumstances, two input signal sources, the generated currents have the same magnitude and the same direction. When the two currents pass through the resistor REE at the same time, that is equal to double the resistance REE. Rewrite the circuit form to the shape shown in the picture. It can be seen that the resistance of each emitter at this time are equal to 2 times the REE. For common mode circuits, its input resistance is the same at each end. Ri is equal to RBE plus 2,1 plus beta REE. Common mode output resistance is equal to RC. Single-ended common mode gain is equal to the ratio of the output voltage at each end to the input common mode voltage. It can be seen that it is equal to one of the half circuits. The amplifier gain represented is RL out of 2 REE. Since the common mode equivalent circuit is its input signal, is in the same size and same direction, so the voltage generated at the two output terminals also existed. Same relationship in the same direction and size. So, its common mode voltage is equal to 0. Common mode voltage gain is also equal to 0. Let me introduce the concept of common mode rejection ratio. Because the output voltage of the common mode signal is 0 when the output is double-ended, so we only consider single-ended output use. Half of the differential mode gain compared with common mode gain. We call this ratio the common mode rejection ratio, written as KCMR when we put differential gain AVD expression of common mode gain AVC, substitute into the common mode rejection ratio formula. It can be obtained that the common mode rejection ratio is approximately equal to product of transconductance Gm and resistance Ree. It can be seen that the greater the Ree, the better the common mode rejection ratio. However, if the Ree increases, the current Ree will decrease. That has high requirements on power supply. So, we will introduce the current source bias method in the following up. For common mode rejection ratio, we can also use decibel units to express. When expressing the common mode rejection ratio in decibel units is equal to 20 times the base 10. Take the logarithm of the common mode rejection ratio. After we analyze the differential mode performance and the common mode performance, we can synthesize the final output signal. The single-ended output voltage VO1 is equal to the sum of the common mode output voltage VOC and 1 out of 2 differential mode voltage. VO2 is equal to the common mode output voltage minus 1 out of 2. Differential mode input voltage. When we introduce the common mode rejection ratio into this expression, we should eliminate the common mode gain AVC, only retain AVD and the common mode rejection ratio. We will get the following formula. We can also see from the formula, the greater the common mode rejection ratio, the less common mode input signal has on the output. At double-ended output, differential mode voltage is equal to differential mode gain, multiplied by the signal difference between the two inputs, and the common mode voltage is equal to 0. Finally, we use a problem to consolidate what we have learned today. The picture shows a differential amplifier circuit. The null condition of the circuit parameters in the circuit have been given. Input signal at this time, Vi1 is equal to 23 sine omega t microvolt. Vi2 is equal to 0. The problem requires that the output voltage be VO2. That is the collector voltage of the T2 tube. First of all, we should find the static operating point of the differential amplifier. You can get the size of each transistor's ICQ1 and ICQ2 current by solving the IEE. Then we make two arbitrary input signals, Vi1 and Vi2, expressed in the form of differential mode signal and common mode signal. Transconductance Gm is equal to the current collector current ratio with thermal voltage Vt, so that we can find the gain of the differential mode circuit AVD is equal to GMRL. Common mode gain AVC is equal to RL out of 2 Ree. We can find the common mode rejection ratio equal to GMREE. Substitute it into the expression of VO2. It is equal to -1 out of 2 AVD times VID minus 1 out of KCMR. Then multiply it by VIC to find the final result. Okay, that's the end of this class. Thank you.